I'm going to hand over to Pete Evans from BP and Gerard Bottino from Baker Hughes. So Dr. Evans holds a PhD in geochemistry and an MBA in technology management. He joined BP 11 years ago and has worked on a range of environmental technology challenges, including water quality, radioactive waste, and greenhouse gases. Before joining BP, he was a senior scientist for the UK's chemical meteorology program and worked for Imperial College London. He is the technical lead behind BP's aim to measure and reduce methane emissions, part of BP's aim to reach net zero. And Pete is based in London. And our other guest speaker today is Gerard Bottino, who works for Baker Hughes. Gerard joined Parametric in 2008 as the Flow Product Specialist Europe, Middle East and Africa region, and served since 2014 as the Global Flow Commercial Development Leader and Technical Support. He started his career in 1990 in the process industry after his MSc in Scientific Apparatus. Before joining Parametrics, he had several technical and commercial roles within various industries, inclusive of more than 20 years in flow measurement. And with that, I will hand over to the two of you.
Marvellous. Thank you very much. Maybe if you jump to the next slide. So this is a little bit of a tag team presentation between Gerard and myself. I'll set the scene briefly. Gerard's going to give a deep dive into a particular technology that comes out of Baker Hughes, and I'll finish up with some discussions about work to verify and provide sort of insights and accuracy behind some of these methods. But it starts with really a thank you to Jasmine. It was a super introduction to the topic of flaring and why flaring matters. And of course, the best flaring is the flaring that never happens, where you bring the flaring volumes down. But where flaring is required for a variety of reasons, there's a requirement then to make sure that the total greenhouse gas emissions, including methane, are managed and minimized as much as possible. And with that in mind, the Methane Guiding Principles put out a tool about 2 years ago now that Gerard and I and many others worked on to provide a little guidance around the various things that come into play when thinking about managing flaring, because from a methane point of view, possibly more so than any other source or principal source of emissions, a flare is a complex interplay of the design of the facility, the volume of gas involved, the composition of the gas being flared, the design of the flare itself, the environmental conditions in which it's operating, and all of these things feed into this critical matter of how efficient the combustion actually is. And what might seem on paper a relatively small shift in the combustion and destruction efficiency of the flare can have quite substantial impacts on the overall amount of methane associated with a facility. But there isn't one size fits all. There's no singular solution to this. And hence the toolkit was put together to walk people through a number of those options and a number of the technologies which can come to bear in order to manage the methane from flaring. One part of which is how you attempt to measure the combustion and destruction efficiency of the flare. And what Gerard's now going to do is talk you through one particular technology which is suitable where you have flares with significant amounts of metering and data on their performance, such as we would quite often find in our own operations, both onshore and offshore. The link to the toolkit's there on the slide, but with that, I'll pass over to Gerard and I'll speak to you again in a couple of minutes. Gerard, over to you.
Thanks, Peter. And again, you can move to the next slide, please, Jasmine. So indeed, to set the tone, it's a very long story that started in the 80s, where people started to look into the efficiency of flaring for the very, very good reasons that Jasmine highlighted in her introduction. Sorry. So these kind of study started in 1983 from the first EPA publication around these efficiencies. So back then it was kind of estimated that flares were running into the 98% destruction efficiency. So just to clarify one point, there's very often two terms being used. One is combustion efficiency, the other one is destruction and removal efficiency. They are not exactly the same. So DRE will account for soot, while CE does not. So DRE tends to be on the slightly higher side than CE. But DRE is the most common one that is utilized. So DRE was meant to be running in the 98% efficiency. So which means that you have a 2% methane slip to make things pretty simple. But further research ended up having more different interactions with environmental conditions. The biggest one being the crosswind. In other words, if you have no wind, or if you have, let's say, 15 meters per second wind, everything else being equal, the efficiency will reduce. So additional research were carried over and data were collected. If you look at the sketch, that is fairly old, but that was one of the first that was conducted with something to collect the plume from the flare stack and analyze the plume to see what the components were post combustion. So at the same time, the flare tip manufacturers worked very diligently to optimize their flare tips, and it is well understood and known that those flare tips by design can have a DRE that is way over 98%. At the same time, there are also other challenges that depends on the way flares are operated. To Peter's earlier point, if you have what we call a non-assisted flare, mainly seen in upstream operations, where there's no supplemental gas because the gas itself is rich enough, and you don't have a steam assistance or air assistance, it's pretty good. So unlike on the mainly downstream assets where there's steam to optimize the combustion when the gas is too rich, they tend to oversteam, which kind of reduces the DRE and CE, while they may assume that the DRE and CE are in the 98%. So there are a lot of dynamics around that that needs and they need to be accounted for. So with this in mind, if you go to the next slide, when the EPA issued the so-called MACT rule, or also known as the refinery sector rule in 2016, as Panametrics, a Hughes business, we started to work on a system to ensure that the flares downstream, so in refineries essentially, were operating at the given 98% or 96.5% when it comes to combustion efficiency. So this Flare.IQ system was developed using what we call a parametric model, which means that it uses existing data sets that have been collected and put into algorithms. And over the course of the implementation of the solution, it has been tweaked and improved. And I must also say that with the very close collaboration we have with BP, Peter and his team, we have really enhanced the algorithms to get to a better performance and try to minimize the potential offsets and biases. So it exists, and as you understood, it was developed originally for assisted flares. I will come to that a little bit later on another slide to explain how it works. But as far as BP is concerned, it has been essentially deployed on upstream assets, which to us makes plenty of sense, because if you look at the data from the World Bank or the International Energy Agency, you will see that most of the flaring occurs on the exploration and production assets. So if you go to the next slide, the way it is implemented on an upstream asset that is non-assisted is fairly simple. It's very simple, but you need to have some prerequisites. The big one is to ensure that you have an ultrasonic flow meter measuring the flow of the flare. So thankfully, for I would say 99% of the conventional fields, that does exist. It's very rare that you do not find an existing flare meter to measure the flow rate of the flare. It might be a slightly different story on non-conventional fields where it's much less deployed. So providing you have it, you have the needed infrastructure to start implementing the Flare.IQ system. So whether you use the Flare.IQ to connect with the control system of the customer via a Modbus communication, if you do what
Gerard, you've been muted.
I didn't mute myself, but someone did it, maybe by accident. Anyway, so as I said, if you can do one more click, so whether you use this industrial computer that is an Advantech, or you use the what you call the System One, that's also from a sister company within Baker Hughes called Bentley Nevada. So in the BP assets, Bentley Nevada System One is already in place. So it was beneficial to use the existing hardware infrastructure and only feed the System One with the Flare.IQ logic. So with the Flare.IQ logic in place, it collects from the flow meter the volumetric flow coming from the flare line, as well as the speed of sound calculated by the meter from the gas mixture. So from the speed of sound, we're going to compute a lot of data. We don't have time to go into the details there, but from the sound speed, we're going to go to the molar weight. We're going to go from the molar weight to the net heating value, and from the net heating value, we're going to go to the CE and DRE. As you rightly said, it's not good to flare. So we see more and more assets where there's flare gas recovery in place or a usage of the flare gas instead of flaring it, which makes perfect sense. And what you need to prevent from a safety standpoint is for air to be sucked into the flare stack, because air contains oxygen, and if it mixes with hydrocarbon gases, and if there's a spark, so we have a big problem. So in order to avoid this, you tend to purge. It can be an hydrocarbon purging, but it can be nitrogen, which is seen most of the time. And if this nitrogen purging does exist, then you need to account for it, because nitrogen has a sound speed, it has a molar weight, but it has no calorific value. So we need to make sure the algorithm is fed with the content of nitrogen being fed so that it can be compensated for. In some assets, an online analyzer exists, and if it does, then we're going to feed the data from the online analyzer into the algorithms so that we get more precise gas composition to run the computation. As you can see from the screen, there's also the wind speed that is taken into account, and thereafter the algorithm runs this calculation and then feeds back to the system the outputs. So now, if we were to use the flare assisted setup, it complexifies the system a little bit, because on top of having the schematic as seen on the screen, you're going to get a supplemental gas line to increase the calorific value in case the gas is too lean, as well as a steam line or more than one steam line going to the flare tip to provide more oxygen if the gas is too rich. In those lines, it's very common to have control valves, and those control valves also will need to be known where they are in terms of positioning for the opening. And the Flare.IQ system will also look at the data and provide the set points to the control system for the control system to trigger the opening of the valves and optimize the destruction efficiency and the combustion efficiency. So, but staying on the upstream assets, if you go to the next slide, you will see that what an operator will see from the control room. We circled the key outputs because the flare inputs in terms of the flow rate, sound speed, etc., might be of interest, but ultimately what the people we're gonna be interested in will be the combustion efficiency, the DRE, the volatile organic compounds, the carbon monoxide, carbon dioxide, and carbon dioxide equivalent. So the difference, as you understood, is that you take into account the methane slip. So this is the kind of interface that is available from the control room to deal with the emissions. So if you can go to the next slide, it will show the details that Peter will gonna carry over.
Very good. Okay, so if I carry on the discussion, maybe if we cut to the next slide to because that one has sound effects. So as one of the interesting challenges that we then face with deploying systems for measuring the combustion and destruction efficiency of flares, and this is also true for a number of other critical methane measurements, is that it is ultimately the responsibility of the operator to be able to demonstrate the accuracy and the traceability of the measurements that they are using. And this creates an interesting challenge in the case of flare efficiency, in that there is no universally adopted, internationally recognized standard by which the combustion of flares is measured, against which the performance of tools like Flare.IQ and a number of other rival systems entering the market can ultimately prove their accuracy. And so earlier on this year, in collaboration with Baker and with Gerard and his colleagues, we set about conducting a series of verification tests on Flare.IQ using what is basically a modern variant of the experimental technique that Gerard talked about that was developed in the 1980s, in which an extractive device is used to take samples of gas from the combustion zone of test flares and send them to a mobile laboratory for sampling. Of course, it has to be a technique that works for a range of flares. There are many hundreds of different flare designs out there. And in this particular instance, we worked on 3 test cases: what I would call an ordinary straight pipe flare, a single tip sonic flare where you have accelerated exit velocities, and then a multi-arm flare, as you can see on the screen, and use these to look at the performance of Flare.IQ against laboratory analysis. And if you pass to the next slide, what this then highlights is why these systems for measuring combustion efficiency are so important. The black dots on the screen on the left-hand side are the reference measurements, and the red dots are the measurements by Flare.IQ. And of course, as part of a verification campaign, the plan was to make sure that these numbers align. But what you can also see on here is why these sorts of measurements are so important. The x-axis on the bottom of the graph is plotting the composition of the gas, and the destruction efficiency is on the y. And if you could plot this and show this in 3-dimensional space, you would also have to be thinking about flare volumes and also critical environmental effects like wind. And what you can see is you can go from very high levels of efficiency in excess of that historic 98% figure that people have used, down into very low destruction efficiencies very rapidly. That transition occurs very quickly when things like the heating value of the gas drops too low, or the wind speeds pick up. And understanding that transition and making sure that your flare is being monitored and you keep yourself out of that zone is where continuous systems have their role. And of course, the composition, the flow of gas changes significantly on a production asset, and we're certainly not in control of the weather. And when I look at our assets in places like the North Sea of the Gulf of Mexico, we have very high winds that blow in at times, and we have to think about what they do to the performance of our flare and include that in our ultimate reporting. And what that results is a ongoing continuous track of how that flare is performing 24 hours a day, 7 days a week, 365 days of a year. If you go to the last slide, what you're then seeing is an example of one of these tracks. This is from one of our operated facilities. Oh, go back to that, that's the one. And what you can see in this instance is what has been seen in a lot of the sort of detailed studies of flare design, which are finding their way into the press these days, where this particular flare is operating at a significantly higher destruction figure than that classic 98% value. But it's not a constant. It does vary with time, and this was under relatively benign conditions. And being able to track those changes means that we can accurately figure how they feed into our reported total methane emissions, rather than working off a single value. And that means that the interventions that we might need can be targeted. That might involve changing the design of a flare in some cases, but more often than not, changing the way that we choose to operate it in order to make sure that we maintain the combustion that we need to minimize the methane emissions, but also keep a track of very important things. We started this conversation by talking about flares are ultimately a safety feature. Well, a well-combusting flare is also a safe flare. And being able to track these things in real time, particularly where in a world where we're bringing flaring volumes down, is very important. So with that, I'll pass back to Gerard, who'll just give us a brief summary, and thank you for your attention. Gerard, do you want to bring it home?
Yeah, thanks, Peter. Yeah, so just a few takeaways there. As Peter highlighted, this is something that runs live and provides continuous emissions monitoring. The technology is already there in place, providing you have an ultrasonic flow meter installed, and this is kind of doesn't really matter what the brand is as long as it delivers to the performance requirements. It's an in situ system, so it means, for instance, in the example shown by Peter, we could see an LP, so low pressure and a high pressure flare, which is typically seen when you are on an FPSO or an offshore platform. And those flares are getting next to each other, and they go into a single boom, and there's one flame. So it can be extremely challenging to distinguish what is the LP performance from the HP performance if you were only looking at the flame, because there's only one flame. So in this instance, you can actually distinguish one to the other. The other point of interest is that the oil and gas methane partnership, where few operators are participating in, have defined some different levels, and does accept the parametric model as a possibility, and based on the testing that we've done, it's kind of promising. And it's also something that is not very complicated to deploy in the field. The people at BP, Peter and his team, can talk about that better than me for sure. But this can be deployed pretty quickly, providing the infrastructure does exist. And the fact that we've done these tests jointly with BP, I think it will give credit to the technology, because as Peter highlighted, we are lacking a reference or a standard to see what is the gold standard. It doesn't exist as of yet, because this market is just being completely new and is in its infancy still.